Hi, my name is Cody Welch.
My name is John Lenz.
And I'm Kyle.
And we're here at the Lamar Pump Lab. This is our Reynolds experiment for Dr. Packey. So what we have here is a clear container full of pond water with some food coloring where we test the different conditions of laminar, turbulent, and transitional flow and clear PVC.
With that, we're left with a question. What exactly is Reynolds number? At its core, the Reynolds number is a dimensionless quantity that helps us to predict how a fluid will behave when it flows. Specifically, it tells us whether the flow will be smooth and orderly, which is what we call laminar flow, or chaotic and mixing, also known as turbulent flow. Alternatively, it can also be seen as the ratio of inertial forces to viscous forces in a fluid. When the Reynolds number is low, viscous forces dominate and the flow tends to be smooth. When it's high, the inertia dominates, which leads to chaotic and turbulent flow. In practical terms, the Reynolds number is incredibly useful for engineers because we were able to use it to design everything from pipelines to airplane wings to medical devices like blood flow sensors. Reynolds number is also essential for scaling experiments. If you want to create a model to predict the behavior of a real system, the Reynolds number of the scale model and the real system must match. But now we are left with another question. Where did this idea come from? The Reynolds number is named after Osborne Reynolds, a British engineer and physicist, who first introduced the concept in the late 19th century. In 1883, he performed a famous experiment where he injected dye into water flowing through a glass pipe. He observed that at low velocities, the dye moved in a straight line, indicating a laminar flow. But at higher velocities, the dye broke up and spread out, signaling turbulence. Reynolds then realized that the transition from laminar to turbulent flow depended not just on the fluid's speed, but also on its density, viscosity, and the size of the pipe. He combined these factors into a single dimensionless group, which we now call the Reynolds number. Today, his work forms the foundation of modern fluid mechanics. In almost every engineering project involving fluids, Reynolds number is one of the first things we calculate. In short, Reynolds number is our key to understanding and predicting fluid behavior. Its discovery completely transformed our ability to design safe, efficient systems across countless fields. And that leads us to today, where our group is trying to recreate Reynolds' famous experiment and observe laminar, transitional, and turbulent flow within our setup. For our Reynolds number experiment, we constructed a straightforward but effective test setup designed to observe and classify the different flow regimes inside a circular pipe. The main components of our apparatus included a water reservoir, which provided a continuous supply of fluid for our testing, a dye reservoir, which allowed us to inject dye into the flow to visualize the different flow patterns, a 3D printed bulkhead, which played a critical role as it served two functions. It secured the viewing tube in place and precisely centered the dye injection needle to ensure consistent and accurate dye entry into the flow. Our setup also included a clear viewing tube where the actual observations of the flow behavior were made. This tube allowed us to visually identify the nature of the flow, whether the dye remained in a smooth or broken apart stream. And finally, our setup included an outlet ball valve located on the downstream side, which allowed us to control the flow rate to achieve either laminar or turbulent flow. Here's what our setup looked like when it was all put together. Please excuse the pond water, it was all that was readily available. With that, we can get into how the experiment was conducted and show a little footage of Reynolds number in action. We begin by looking at the viewing section. This is where our dye is going to come out, and we start a timer with the ball valve fully open because this is a turbulent trial. As you can see, the dye is mixing and cutting because the velocity in the pipe is very high, so it means we have a high Reynolds number. We continue this for a set amount of time, and after I stop the timer, we also close the valve, and then we measured the amount of flow that came through the pipe over the course of the experiment. This process was repeated a total of 5 separate times, twice for turbulent flow, once for transitional flow, and then twice for laminar flow. Here you can see a couple images from the results. We have turbulent flow, which is mixed. We have transitional flow, which is somewhere in between smooth and mixed. And then finally we have laminar flow, which is a smooth line. With the experiment complete, it's now time to get into the calculations. Let's walk through how to calculate the Reynolds number for flow in a pipe using the steps shown in this diagram. First, we begin with the volumetric flow rate. We acquired this through our testing by measuring the volume over a period of time. From this, we're able to calculate the average velocity of the fluid using the formula velocity equals the volumetric flow divided by the cross-sectional area. In this case, it's the cross-sectional area of a pipe. The modified formula shown in the image simplifies this relationship, where we have 4 times the volume that we measured times the power of 10, because we're converting milliliters into cubic meters, divided by time in seconds times pi times the diameter squared. Next, we determine the hydraulic diameter, or DH. For a circular pipe, it's fairly simple. The hydraulic diameter is just the diameter of the pipe. Then we determine the kinematic viscosity of the fluid. Now, this factor depends on the temperature of the fluid, which we recorded before each of our tests. From there, we were able to go into the NIST databases and find what the kinematic viscosity of the fluid is at that temperature. Then finally, we're ready to plug this all in to the Reynolds number formula, which is Reynolds number equals velocity times the hydraulic diameter divided by kinematic viscosity. This dimensionless number helps us classify the flow regime. As shown on the right side of the image, if the Reynolds number is below 2000, the flow is considered laminar. If the Reynolds number is between 2000 and 4000, the flow is considered transitional. And then finally, if the Reynolds number is greater than 4000, the flow is turbulent. Based on actual calculations from our experiments, the results table shows a range of flow conditions and their associated Reynolds numbers. From the laminar values, we got around 500. And for our turbulent values, we got results exceeding 5,000, with our transition being just above the 2,000 limit. In conclusion, this experiment successfully demonstrated how the Reynolds number can be used to classify different flow regimes within a pipe. By combining the visual dye injection with quantitative flow measurement readings, we were able to clearly observe the transitions and calculate the Reynolds number that matched these theoretical expectations. The experiment reinforced the practical and theoretical importance of Reynolds number in fluid dynamics and engineering design, and we were able to gain a greater understanding of Reynolds number through this hands-on approach.